Also to meet you, and you know how wonderful Mayor's presentations are, so let's hear it.
Thank you, Mike. Again, another opportunity to thank Axel and Raphael. I think this was one of the most exciting meetings here. I think that's really, we learned a lot about chirality from different aspects. And I would like today to present some studies about using racemic architectures as auxiliaries for mirror symmetry breaking. One of the studies is quite old, but I decided to present it here because after listening to the theoreticians about that, I would be very happy if somebody after that would be willing somehow to present, to simulate some of the experiments which we have done. Now, in the lecture of Professor Kagan and Professor Soai, they say that when you're taking a molecule which is achiral, which has two pro-chiral faces, like this ketone, if you react this molecule from one face, you can get one enantiomer. If you get this reaction, this molecule acting from the other face, you're getting another product. And one of the purposes in asymmetric synthesis to find some ways, taking the ferrocene, a bulky group from one way, chiral region, and trying to block one of the particular faces in order to obtain an asymmetric synthesis. Now, I think that this point can be also extended to three-dimensional architectures, to much larger systems, and then there one can perform and one can utilize this point much, what is that one? Okay. Let us, because the problem is that the early days, the racemic architectures presumably were more abundant than the homochiral one. We have heard here about experiments of Kornobal, about Viedma, and also Wim, using enantiomorphous crystals. But when I talked to Wim, he told me that they've synthesized at least 20 compounds, right, Wim? Until you find some of these enantiomers crystallizing and undergoing spontaneous resolution. We have also experienced similar system a number of weeks ago when we were doing absolute asymmetric synthesis, going and synthesizing. But the point is that the centrosymmetrical crystals are much abundant. For example, if you consider crystals, they can pack in 230 different space groups. But only 65 of these space groups are enantiomorphous. The rest are racemic. And even among these 65, some two enantiomorphs, some of these groups are actually represented by different space groups. So even this number is even lower than that. Therefore, the probability of racemic or chiral molecule to crystallize in a non-enantiomorphous crystal is much larger than crystallizing in the enantiomorphous crystals. And then we can ask ourselves whether this class of crystals, which are achiral, are really playing some role, or could have played some role in this process of symmetry breaking, mirror symmetry breaking. I mean, we have seen McBride going and curving for the quartz crystals, searching for the quartz crystals which are on the mark. But there are many others. If you take, for example, calcite, you take gypsum, all these are centrosymmetrical systems. And the question is there a way that one can take advantage of these centrosymmetrical architectures in the various steps of symmetry breaking? And I shall bring you today two examples. One is the old one, and the other one is actually what we are trying to do today in the case of peptides, where we are taking advantage of racemic architectures in order to be not enantiomorphous systems in order to break symmetry. Well, what is unique about such kind of asymmetric architectures? Here we have a racemic architecture, okay? And if you take a racemic architecture, the bulk of that is achiral, because here you have asymmetric, you have centers of symmetry in the bulk, and therefore you have molecules of unit of both-endedness. But as you move to the surface, the surfaces which delineate these architectures are homochiral. Now, the advantage, the difference between this architecture and this molecule is that this is a macroscopic system. And if we are growing, let's say, a crystal, this crystal has to be somewhere. It may be deposited maybe on a given surface. And if it's deposited on a given surface, we have a very nice way how to assume to generate asymmetric synthesis. Because here we have to use some kind of a group that blocks or hinders the approach of the reactant from that particular part. Here, if you deposit that crystal on a surface of some kind, you're actually exposing the other surface to the environment, and you have created you have homochirality. Actually, the central symmetrical crystal is actually exposing one of its homochiral faces to the environment. Now the question is, if you want to utilize this particular property, then we have to design some new experiments which are different from the experiments of the enantiomorphous system, in other words, to be able not only to generate chirality, but also to amplify chirality. And I shall try to bring an experiment which has all the elements of the Frank model. Has all the elements of the Frank model in the generation of homochirality, and I feel that this system is relevant because it contains glycine and racemic amino acids. Glycine was the major component which has been found in the Miller experiment. Glycine was a very important component in the Wachter-Hauser experiment. And the DL amino acids are also formed in different and various ways. Now the question is that these amino acids were racemic, and the question is, if they were racemic, can we use glycine as the major component, a molecule which is achiral, which crystallizes, as we shall see, in a non-chiral crystal, in order to be able to separate spontaneously between this racemate in a given experiment in water. And therefore I shall take to see that we have actually able to perform such an experiment which contains three different elements which we have tried to analyze and to investigate separately. Actually, this type of experiment has inspired us to go to different directions and to find three different problems independent to this problem of homochirality, and I shall see how we can combine these three particular factors in order to design an experiment of spontaneous mirror symmetry breaking. The first problem is the formation of mixed crystals. How a mixed crystal is formed. And we shall see immediately that there is a process of mirror symmetry breaking by crystallization. If you are moving two-component crystal, if you crystallize them, the mixed crystal, although the host crystal may be centrosymmetric, but the mixed crystal is racemic. Symmetry and reduction in symmetry. The second problem that I shall try to discuss is the question of the air-water interface and what is happening in the air-water interface. And the third one is understanding the early stages of crystal nucleation. The second problem which I shall try to discuss will be also the question how we can use centrosymmetrical crystals to generate homochiral peptides. And then finally, I shall try to raise the question of racemic beta sheets, which have been proposed by Pauling in early studies, but I shall try to see how we can take advantage in order again to break symmetry and to generate homochiral peptides. Again, coming back to this particular experiment, I shall express the experiment in a very simple one. You take a solution of all the racemic amino acid in water, and you take glycine as a major component, and you start evaporating the solution. At the end of this, you find a crust of glycine crystals, which contain only one kind of amino acids, whereas the solution contains the other amino acid. This will be the final result of this experiment. Now, it contains three different elements: reduction of symmetry of mixed crystals, self-assembly of amphiphilic alpha amino acid at air-water interface, and an anti-selective inhibition of growth of the glycine crystals by the alpha amino acid. This is an old study, and I've done this with my colleagues, as you know, Isabella Weisbuch, Lia Dadi, now professor at the Weizmann Institute, the late Ziva Berkovich, Edna Gatti, and my friend Leslie Dezerovich, with whom I've collaborated for 20 years and more.
More.
Okay. Now let us go to the question of reduction in symmetry of mixed crystals. Let's say I'm preparing a crystal and I'm trying to make a co-crystal by crystallizing one crystal with another molecule. And I'm forming a mixed crystal of the system.
You got that with me yesterday.
I know. Well, I'll see what they do.
This one's it.
This one?
Plug this back.
Oh, here it is.
Oops,
Okay.
you have to back up.
Okay, I go back. So let us now look to the crystal. I say glycine has three different polymers, alpha, beta, gamma. If you crystallize glycine in water, you're getting the central symmetrical crystal. The beta and gamma polymers are enantiomorphous, but if they don't grow in water. If you grow them in water, you are generating this alpha form of glycine. This is a central symmetrical crystal. As you can see, these crystals have centers of symmetry. Now, the molecule of glycine is achiral because it has a mineral plane, because the two hydrogens are actually what this law will call enantiotopic. They are actually related to one another by a mirror plane. But as you crystallize glycine in the crystal, glycine assumes a chiral conformation in the crystal. Okay? But let us now look on the unique property of this particular crystal. It has centers of inversion. Therefore, the crystal is not chiral. But if you have layers of R molecules, because the conformation of the glycine crystal is chiral, the molecule in the crystal is chiral, you have a layer of R molecules, and you have a layer of S molecules. You have a layer of R molecules, and you have a layer of S molecules, alternating. Now let us concentrate on the vector CH. Let us concentrate on the vector CH of these glycine R molecules. Of all these vectors of R molecules, all these vectors are pointing toward the plus B direction. Whereas if you look on the vectors of the S molecules, they are pointing toward the minus B direction. We coined the term enantiopolar, because central symmetric crystal is not polar, but we say it is polar with respect to each particular enantiomer. And I think this property is quite important, because we shall see immediately that if you have a molecule of R amino acid, all the alpha amino acid except proline, they can be recognized by this particular surface O1O, but they can be recognized only by the R layers. They cannot be recognized by the S layers, because would such a molecule would like to come and to sit in one of the R layers from the minus B direction, because of this R group, this molecule will not be recognized by that particular surface. On the other end, what is happening? The S molecule comes from that particular site, and it can fit very well into the S layers of this particular crystal. So, this is now what? There is a kind of recognition. This crystal can recognize the homochiral faces of the glycine crystal, can recognize between the R molecules and the S molecules. Now the question arises, how we build up a mixed crystal? Let's say it again. So let's say another experiment. This is again the same crystal. We can monitor this by the morphology. If you grow the crystal in pure water, you get a bipyramid. But if you grow this crystal in the presence of R amino acids, you are getting an half pyramid, which means that this surface has reacted with the R amino acids, and this phase has been now very well expressed. You know that if you impede the growth of a certain phase, you actually increase the surface area of that protein. And then what you do the next one, if you take the S amino acid, you're getting an enantiomorphous chirality. And then if you do this with the DL, you generate actually a plate of the RS. You point at Pasteur. Pasteur did a very nice experiment when he separated the tartaric acids. when it's separated tartaric acid, and you consider that the molecules are chiral. But Pasteur was not able to tell the absolute sense of chirality of the molecule on the basis of the morphology. And when X-ray started, because of the Friedel law, it was difficult actually to tell to differentiate between an enantiomorphic L and D. And until Bijvoet came in Holland, actually in 1948, when applied anomalous scattering, was able to tell the absolute configuration. But here, a regular X-ray diffraction method can tell you what is the absolute sense of chirality of the two surfaces, and therefore these morphological changes can tell us the absolute sense of chirality of the R and S amino acid just by measuring the morphologies of these crystals. But now we start asking, where are these amino acids? Where they are? Are they just on the surface, or these molecules are going into the crystal? So what we try to do, very primitive experiments, we took these plates, we took a razor and started grinding, and taking some of these molecules from the O1 phase and from the O-1 phase, and submitting this to a chiral HPLC to search for the other amino acids. Now we have taken here an example of glutamic acid, growing this crystal in the presence of DL glutamic acid, and you see that on the top you get only R-glutamic acid. The S is missing. And if you're taking this on the other side, you can see that you have the S-glutamic acid. So this is a very important experiment. You grow crystals of glycine in the presence of DL amino acid, and the DL amino acid, and this is 0.1%, okay, in other systems can be higher, in other crystals, but it's 0.1%, you can really have separation. You have spontaneous separation of the DL amino acid within the crystal of glycine. Okay? Now, what I said before, if you take entire crystal, of course you get DL. And this is another experiment. If you now take this crystal, or you take the crystals which have been grown at the surface, either at the glass water surface or at the air water surface, and you analyze, in this case we just for representation, we have used para-hydroxyphenylglycine, glutamic acid, DL methionine, and you can find that if you grow that crystal of glycine at an interface, be it at the water-air-water interface, the crystal grows unidirectionally into the water and picks from the foodstock only, in this case, the D-amino acid, depending on the orientation of the crystal at the air-water interface. Would I try to turn over the crystal, that particular crystal, with the other phase, I will include in the crystal the opposite enantiomer. So now the question arises here now, this is not sufficient. This is another example. If you take two enantiomorphous crystals, sometimes you get L, sometimes you get D, and of course if you take a large number of crystallization, you are not getting any kind of asymmetric induction. Okay? In other words, this experiment from growing a centrosymmetrical crystal at an interface is a subgroup, if you like, of the enantiomorphous crystal grown in the water system. Now the question arises, how we can transfer information? Because let us assume that I have an atom crystal. This is what you wrote in your early states, but this is not politically correct. The first crystal might call it atom crystal. No, politically not correct, and some people recently have said that one should call it the Eve crystal. But since I'm married to a teacher of Bible, I went to the Bible and looked in chapter 2 of Genesis. And then what was written in chapter 2 of Genesis, God created Adam, which in Hebrew means a human being, unisex.
But maybe
Not the sex, unisex.
the Bible was also not politically correct.
Yeah, that's right. Okay, but it is only in the chapter 3 when they took that, he become, let's say, he separated between the two. But anyhow, you can use the Adam. I prefer to use the Adam because if you use the metaphor, you should be somehow linked to the root of that term. So the question is, if you start growing a single crystal with one orientation or a number of small crystals which has a bias to one orientation, the question that we are asking, how you can force the new crystals that are going to grow later on will be with the same orientation as the first crystal. And if they are going to be with the same orientation as the first crystal, they should continue to pick up from the footstock the same amino acid of the same endedness as the first crystal. Okay, this was actually the question. And to make a story long story, for example, I just brought here some studies, the recent study by the Ureo and Hazen, that they show how crystals of calcite grown in the presence of aspartic acid can affect these particular surfaces of these minerals. But let's return to our point. Again. Okay.
Did you try back?
Let's try back.
There we go, but now you have to back up some.
Okay, that's it.
You go back.
So what we're trying to elaborate an autocatalytic process for the deracemization of the racemic alpha amino acid present in solution. Now the second point, after neural symmetry breaking, we were asking what happened to the hydrophobic amino acids which are residing at their water interface. If you perform a macroscopical measurement of surface tension, you can notice that at least 30 to 50% of these amphiphilic molecules are residing at their water interface. But we ask ourselves the question, what is the structure of these clusters? And then would such clusters have a function as nucleating systems? Because a lot has been raised in this conference, whether there are clusters which are responsible for crystal nucleation. Okay. So we did the following experiment. We tried to grow crystals of glycine by putting some amphiphilic amino acid like leucine. You put 1% leucine to the solution. You take the glycine with the DL amino acid and you put 1% L-leucine to the solution. And what you observe that the surface, by cooling down, you observe that the surface is covered with crystals. And these are crystals of glycine. But if you inspect the symmetry of these crystals, because these crystals are floating in 2 dimensions. They are not turned over. They are just floating in 2 dimensions. And you can immediately notice that these crystals have a 2-dimensional chirality. Like if you're going into your park, in the parking lot, you go in one direction, but if you want to go in another direction, you cannot do it because there's opposite chirality. Let me just illustrate that to convince you that these are really, if you inspect the crystals, you can see that they are enantiomorphous. For example, these are 2 mirror images with one another. And what happened now here is that if I try to superimpose one on one, no problem. But if I like to superimpose one on the other, it is impossible. And this is because these crystals have a 2-dimensional chirality. Now this was a very simple, I call it a romantic experiment. You just draw the crystals, put some of this, and you get the point. The question is, what the L-leucine, what 1% of L-leucine is doing to try to orient these crystals. And by looking on crystal structures of many of the alpha amino acids, valine, leucine, phenylalanine, we notice that all these crystals, these molecules in the crystal, have very similar pattern as glycine. So we assume the following, that if you put some R amino acid, these are amphiphilic amino acid, at their water interface, if they are, let's say, of a given endedness, they should create a cluster where the polar head groups of that cluster are the same as the first layer of glycine. And if they are the first layer of glycine, they should actually serve as nuclei for an oriented growth of the glycine crystal. Okay? And therefore you see that if I have with the R amino acids this crystal will start growing from the R molecules and going in one direction. But as they grow in this direction, they pick up from the footstock molecules of opposite endedness. If I have molecules of the opposite endedness, I create here a cluster which has the structure of that of lysine, but of the S amino acids. And if this crystal starts growing, it will have molecules which will go into that crystal from opposite endedness into these particular crystals. Okay? So what we proposed, this was just an assumption at the time, that these molecules which are amphiphilic, which we are depositing them at the air-water interface, these molecules form a cluster. And this cluster has a function. It is a function for an oriented growth of these glycine crystals at the air-water interface. Any questions, please?
Yeah.
Yes.
When you see these shapes that are all the same on the surface,
Which one? Not.
the glycine crystals, so that you know they're all the same
You
two-dimensional.
know that you asked me that question 20 years ago.
But it says.
I know that two crystals are of opposite centers, that you notice that, and I know that. But the problem is that if the environment...
This is like the joke, right? I tell 23 and you laugh.
Okay. The problem is that these crystals are growing, and there is also the environment somehow may change somehow their morphology. But we have
Because
done
the only way you tell the difference is that one edge grows faster than the other.
yeah.
If they inverted how fast they grew, then one would look like the other.
Yeah, but we
So
can-
everyone must grow with the same relative rates of the two edges.
Yeah, I think that but they grow in a confined environment, and therefore the environment may somehow affect differently the lights. For that reason, we didn't base ourselves only on the morphology of the crystals,
Yeah.
but we also tested this by crystallographically,
Yeah.
and also by this method of HPLC.
You could also do it by birefringence.
Well,
looking
you
through
did
the-
it actually, I remember, in one of the crystals. This was the elegant experiment.
Yeah.
You do it by- but only in some space groups, or specific space groups. We
Uh-huh.
cannot do it in any crystal.
Okay, sorry.
Okay. Okay. So now the question was, we wanted to study in depth the organization of amphiphilic molecules at the air-water interface. And we were very lucky, because just at that time, when we were asking this question, Professor Jens Nilsson, University of Copenhagen, then at Rizzo, and Christian Kerr at Rizzo, were starting the studies in Hamburg to use grazing angle X-ray diffraction. This is what is that. This grazing angle X-ray diffraction, you come with a very intense X-ray beam from synchrotron source, and when this beam is below the critical angle, then you shine the surface which contains the materials, and if you have clusters on this particular surface, you are anticipating an X-ray diffraction. And you might have 2 points, 2 informations. You can get the break peaks, and you can get the break rods. The break rods give you exactly the tilt angle of these molecules at the end and their water interface, and the break peaks can give you the coherent length of these clusters. Now, these are simple molecules relative to three-dimensional crystals, and therefore from this powder diffraction, one can obtain almost the structure of these clusters almost on the molecular level in some cases. So in other words, what we can do now, we can determine the structures of these clusters and investigate crystal nucleation at their water interface by determining the structure of the polar head groups which are attached on the water and the surface from which a given crystal starts growing. And we have several examples. We have, I think, at least a dozen of examples. You can nucleate ice with alcohols by looking at the structure of the OH groups at their water interface and to see how they fit to the crystal of ice. But here we try to do this with the amino acids. It so happens that the natural amino acids don't have enough electrons, so they are not amenable to such kind of analysis. For that reason, we have to elaborate a synthetic program that we synthesize all these amphiphilic amino acids at their water interface, and we tested again the crystallization and the orientation of the glycine crystals, and we found that they are very similar to what we observed with the case of the leucine, valine, and these small molecules, and we say that the structure of these clusters must be very similar and therefore relevant to our investigation. For example, this is a system of diffraction of glutamic acid to which we have attached an alcohol, C18 alcohol, and we have done the R molecules at their water interface, and you see that there is one structure, this racemic compound, in 2 dimension. This is a two-dimensional racemate at their water interface. This is one, the RS, and this is the R-glutamic acid, which has a different structure. So this molecule has not undergone some kind of spontaneous resolution. Other molecules have done that. But even more, if you take 7,3 of RS, you can get a phase separation. In other words, you can take phase separation between the DL and the L. And I think this was very important for us, because if a separation, once you enrich the solution with one of the enantiomers of amino acid, and they actually are in equilibrium with the interface, we thought that these molecules can also undergo phase separation. The DL can give you DL, but the excess of that can give you the L, and the L can induce the nucleation of the glycine crystals from one enantiotopic phase. And this is what we found, that if you have these ends here, they can organize the molecules which are in the water, and they can start crystallizing. And what we have found by this diffraction method, we have found that this layer here is very similar to the first layer of glycine, as we proposed experimentally on the basis of the orientation of the glycine crystals in the system. Okay? So, this was the first part. The second point was, this is the point of inhibition. Because the Frank model has at least 2 effects. One has to promote, and the other one has to inhibit. Cross enantiomeric inhibition. Okay. So now the other part was that if you have such clusters, and you know the structures of these clusters, if you have an additive to the solution, which can be targeted enantioselectively on clusters of one-endedness, and it can interact with these particular clusters, these clusters will decompose. They cannot grow. They cannot cross the critical size. Whereas the other one actually can continue to grow. So this is what we have, the experiment that we have done. We have taken racemic amphiphilic amino acid. So we put equal amounts of DL leucine on the water surface. But we have taken now an hydrophilic alpha amino acid in excess in solution, and we observed the same experiment as previously. So in other words, it was, the chiral molecules which are in solution, they can be recognized by the 2 different orientation of the glycine crystal, and if we have excess of L, we can inhibit, we can delay the growth of the L crystals, and the D crystals can continue to grow. So let me just illustrate it, because we elaborated the general method for resolution of enantiomers by adding additives. If you have, let's say, a racemic system which undergoes spontaneous resolution, the rate of growth of the R crystals and the rate of growth of the S crystals is exactly the same. If I add to this solution an S prime molecule, this S prime molecule can affect the crystal, but it also can affect the nuclei. And then it can actually prevent this nuclei to grow, and then R is larger than KR is larger than KS. Let me just illustrate this with one example. We tried with the company, with the GUSA, they had a problem how to resolve methionine, because there was a difference price between L and DL methionine, and they asked us how we can convert DL methionine into L methionine. And we found that the methionine hydrochloride is a crystal which crystallizes in an enantiomorphous space group. It crystallizes in an enantiomorphous space group. But when you take a single crystal, in other words, if you go to the X-ray diffraction, you see a chiral space group. But if you take a single crystal, and again, we like very much to grind them, right? And if you grind, now if you dissolve it, it has almost a racemic composition. But if you start now grinding in this direction, you can find very high enantiomeric excess. And it is alternative. If you're grinding in this direction, you don't observe an antiumeric excess. Okay? And therefore, we thought these are actually lamellar twins. They are micron large, and therefore they diffract independently. And the question, but you cannot use it for separation of enantiomers, at least by seeding. And the reason for that is that we shall see immediately that these molecules have strong interactions between the hydrophilic groups, but very weak interactions between the hydrophobic groups. And as one crystal starts growing, one lamella starts growing, and if one enriches the solution with the other one, then these faces here can operate as templates for the deposition of the other one. And therefore we are generating actually these lamellar twins. But now if you're heading to this, the additive, and this is the same case with cysteine hydrochloride, and we have valine hydrochloride. But now what happened is, these are the weak interactions here. What happened here is that if you had now a polymer, which is methacrylic acid, to which you have attached lysine, and let's say it is L-lysine, and you add this to the solution, what happened is, then 1% or even 1%, you can remove completely the lamellar twin. You can get 99.6, 99.8% by GC. And in order to explain that experiment, what we are proposing, that you have clusters in solution. It cannot grow, the crystal cannot grow molecule by molecule, but it must grow by cluster, and by having this particular molecule, which can be targeted enantioselectively on some specific clusters of the solution, you prevent their growth, and the other one can grow now nicely. And this process has been elaborated on 10 kilograms, actually. So now the question is, we have now three effects. The first effect is symmetry breaking by the formation of the mixed crystal. The resolution of the enantiomeric DL amino acid within the crystal of glycine. Okay? The second question is, there is the equilibrium, if you like, between the interface and solution. Once we enhance the concentration, enlarge the concentration in solution of one of the enantiomers, we are also enhancing the concentration of that air-water interface. Now, but if you start with a very low enantiomeric excess, you have both of them at the air-water interface. Now the question is, as I say, if I am now starting enhancing the concentration of the red, by decreasing the concentration of the green, the reds are now in excess at the air-water interface, and therefore they can enhance more the crystallization of the glycine crystals with the air layer attached to the interface. But now the ones which are in solution are in excess. These are the green, the red, they are in excess also in solution. And as we start growing these crystals, let's say we can grow these crystals, they pick up. These ones are much smaller crystals because we have less molecules at the air-water interface of the green, but we have more of the red, and at a certain concentrations, this red can prevent the growth of these small crystals from growing, and what we observe, actually they don't grow, and we grow actually crystals of one and the next. And this is actually they've used a molecule of lysine, LTP lysine, which enters to the crystal from one side. It is a color molecule, and you can see that when we use S-leucine, we say that the crystals are white. When we use D-leucine, the crystals are yellow, and they are very thin because they are affected by the excess of the L-amino acid which are present in solution, and these are crystals which are attached to this particular crust underneath. But we can see that we can perform an experiment of the separation of the amino acid, which has the two elements of the Frank model. The molecules which are formed at their water interface form clusters which enhance the crystallization of the glycine crystals with the appropriate orientation, whereas the one which is excess in solution prevent the growth of the other, and maybe there is also some phosphorypening. because these crystals are quite small, and maybe they are also can assist with this particular part. So this is a kind of a Frank experiment, Frank model experiment, which expresses the formation, the separation of the DNA amino acids. Okay? And say the effect can be explained by applying the class polycomb to hydrophobic clusters and induce the nucleation of glycine crystals with a desired orientation, whereas the water-soluble amino acid formed in excess operate as nucleation inhibitors of the nuclei of opposite orientation. In addition, also ripening can operate in the dissolution of the small crystals. So this is another example, extension of the Frank model to centrosymmetrical crystals, not to enantiomorphous, to centrosymmetrical crystals, where they can really induce separation of enantiomers. Now, the second experiment which I would like to discuss is the question of the formation of the biopolymers. It's a big problem, and I think some people believe that it is much more difficult to generate large polymers of homochiral sequence from racemats. We have seen in the lecture of Professor from Auguste that he said that the mechanism for formation of the homochiral peptides can be by what Raphael proposed, racemization. Once you're forming that, in that you have racemization. But what I would like to express now today, the experiment where, and I shall tell the end of the story, and then after that I shall try to explain it, that what we are doing is, we have now an experiment where you're taking DL amino acids, and mixtures of some DL amino acids, and you put them in water, dissolve them in water, and adding carbonylimidazole, which is a replacement of phosgene. Under a bracket shown that you can polymerize amino acid also with phosgene, but we don't like to work with phosgene. And then what you can generate homochiral peptides of homochiral sequence. And again, let us see how racemic architectures can play a very important role here as templates. He refuses. Okay.
Here we go.
Back.
Now forward.
Okay, I think this is something that Raphael showed us in the first day. Raphael, it is true that if you have polymerization of monomers more than 2 components, you have to get what you call the binomial distribution of this. The chains will contain binomial distribution. You show it in different way, but I think we can show it by the Pascal triangle, and where you get the wings. This I learned from you. The wings of the triangle are actually representing the homochiral peptides that are formed. If you take a racemic mixture of 2 components, if you go to the first one, you take dimers, which are RR, RS, SR, SS, whereas the wings of this represent the homochiral peptides. And this also demonstrates that if you go to very high and very long peptides, the wings are becoming smaller and smaller. So there must be some mechanisms by which one can convert racemic mixtures, the polymerization of racemic mixtures, into polymers of homochiral sequence in this system. Okay. The first type of experiment, and that is what we were proposing, was that one way to overcome this binomial distribution is to have some clusters. So the first experiment that we did, we went to the air-water interface, and we took this kind of molecules like N-carboxyanhydride. I think today N-carboxyanhydrides are regarded as real intermediates for the formation of peptides. In Gustav has shown us to that, right? I think Orgel also agreed to that, and Wachtenhauser, I think, also accepted. So these are intermediates.
With G2.
What?
With Z2.
What?
With Z2.
Louise.
With G.
Yeah, I will come also to the work of Louise because we have to. Okay. And then if you deposit these molecules in their water interface, and since we have found that they undergo phase transition, phase transformation, phase separation, and we can determine the structures of the various phases, we thought we might be able to do in a more systematic way the understanding and trying to overcome this particular problem of binomial crystallization. Now, the method that we are using, and this also I shall come back also to Luigi's studies, which is also using this part. We have used that method also for mapping disordering racemic crystals by labeling one of the enantiomers with deuterium. If you label one of the enantiomers with deuterium, the DNL have different molecular weights, and if you go to multi-TOF-TOF, it is possible in this multi-TOF-TOF to actually determine the distribution of the various diasteromeric peptides which are formed. In particular, you can determine the quantity of the homochiral peptides. You cannot separate between different diasteroisomers which have different composition, but you can separate between the homochiral peptides as with the others. Okay. And then let me just illustrate this because I want to come to the others, which is more. Let us take one experiment. If you take, for example, that a non-racemic mixture of one of these monomers, which is amphiphilic, and you deposit their water interface, you may have a separation of territories. You may have the RS formed on one end, and all the excess, or most of the excess, can be actually separated in a different phase. Now, if you go, and this is done on the air-water interface, if the reaction in the racemic crystal goes along the glide plane, you're going to get some kind which is a syndiotactic oligomer. But the excess which is formed, which is present here, will separate in another phase which is homochiral, and within this homochiral cluster, you can obtain homochiral peptides. So let me just show you one example with that, and that is if you take N-carboxyanhydride glutamate, and if you do the X-ray diffraction of the L and of the DL, you can see that they are different. And from this information, it was possible to determine the structure of the two clusters, which are formed in the air-water interface. And you can see that in one cluster, the molecules are related by a glide plane to yield a syndiotactic polymer, whereas the excess of this crystallizes in a cluster which is homochiral. Now what you do, you inject the catalyst into solution, and you collect the molecules from the air-water interface, and you go to the mass spectrum. Now remember again, the wings for each, let's say this is dimer, tetramer, hexamer, the wings represent the homochiral one, whereas the center represent the heterochiral one. And you can see here, for example, that if you look on the letter, which is RS, is much, much larger than 1 to 2 to 1. You see here it is 0.8. Now what is much, much larger, which indicates the RS is formed in excess. Okay, but if you go now to 3,7, you see that the short peptides have a kind of a distribution, but as you go to the long one, you see only 1, and 1 minus 1 are actually formed, which is in a given with this experiment that the RS non-racemic mixture has undergone separation into a racemic one and an antimorphous one. Injecting the catalyst, somehow these molecules have been polymerized, different rates than in the RS crystal, but you were able actually to generate some kind of homochiral peptides. The concept beyond that is that if you have self-aggregation of some kind in the system, you can break binomiality, you can break randomness. So the next problem was, let us go to three-dimensional crystals. It was not a simple conversion to three-dimensional crystals because, I did my PhD in polymerization crystals. I learned this field quite well at the time. And I knew one thing, that if you polymerize a system, a monomer, in a crystal, where the density of the polymer is higher than that of crystal, the control of the crystal in this reaction can be in the stage of the dimer and the trimer. But once the dimer and trimer has been formed, you create a defect in the crystal, and the propagation of this reaction is actually not controlled by the crystal. People in the 60s were very much excited that they can actually more follow the Ziegler-Natta mechanism to get homochiral, to get stereospecific polymers in crystals, but this was a big disappointment. Now, This was a question, and I think this is something which is, a priori, when you know that and you want to do another experiment, you're preventing yourself from doing that experiment, because if you do the polymerization, you're expecting that nothing will come out of that. But sometimes, I learned when I was at Harvard from Harvey Woodward in these night seminars. He always used to say, never forget, never hesitate to do an experiment. If you have a feeling of some kind, please don't do that, because you can do something that you don't know yet. And therefore, when we look on this crystal structure, which was done on the phenylalanine and carboxyanhydride, which was done by Kanazawa and Ohashi in Japan. They published that. Thorin Ohashi is now retired, but he was in the Technical University of Tokyo. And we tried to polymerize the system because we were very inspired, actually, by the crystal structure of the system. If you look in the crystal structure of this N-carboxyanhydride, you can see that there are layers, there are rows of S molecule. This is a racemic crystal. There are rows of S molecule in the crystal, and there are rows of R molecule in the crystal. And then we thought maybe, for some reasons, if you polymerize these crystals, maybe they can give us some chiroteptides. So what we did actually, because N-carboxyanhydrates are very sensitive to water, but what we did, we took these crystals and we put it in water which contains the initiator, an amine. And then, again, we labeled the S with deuterium, the D as it is, and we performed the mass spectrum of these particular crystals, of these particular polymers. And what we found exactly the opposite from what we expected from the experiments which were done on this kind of vinyl systems, or systems like this one, because this also releases carbon dioxide, and the carbon dioxide can also create some kind of disorder at the site of polymerization. But what we found that the short one were not very stereospecific. But as you move, and you could get here up to 25, now we can get up to 25, in some measurements even 30 pit units. And as we move to the longer and longer one, we could see that the wings are actually pumping out. So this behavior was very different from what we anticipated in the early stages. And we asked ourselves, what this may be? And to make a long story short, what we thought was that if once the short peptides are formed, if they self-assemble into beta sheets, and this crystal structure allowed us to see that they can be aligned in a racemic beta sheet. And therefore, if once this beta sheet is formed, now the control of the propagation is done not by the crystal, but is done by the beta sheet. In other words, it could start from the crystal, but it can continue by the beta sheet, and the beta sheet now could actually exert induction, stereosymmetric induction in the ensuing process of crystal polymerization. Okay? And now the question was, what were these beta sheets that we expected in this particular crystal? And from the crystal structure, we anticipated that these are actually racemic beta sheets. That you have a layer of poly R, and you have a layer of poly S, you have a layer of poly R, and you have a layer of poly S. Now the question is how we can differentiate between these, because spectroscopically they are very similar between the treated beta sheet that we found in nature. And the way to do that, we say, let us start the reaction with a chiral initiator, which may be a methyl ester of the amino acids. Now, if it is, let's say, this S will be attached at the wing of this chain, both of the S and both of the R. But the S molecule can fit very well in the S chain, because what I've done, I've changed a carboxy group with an ester group. But if I have an S chain attached to the R, I can affect the near neighbor of this molecule, and this will be some kind of an enantiomeric cross inhibition. This will be because we are forming here clusters, although this will not be exactly an enantiomeric cross inhibition, because if I start with S, I am inhibiting the growth of the S chains, Whereas if I start with R, I shall inhibit the growth of the R chains if it is a racemic. If it is a pleated sheet, the S should inhibit the R chains, whereas the S chain can grow normally. And by analyzing the enantiomeric excess of these particular peptides, we could see that the short one, if we start with the S, and the S, the L are labeled with deuterium, therefore they are the longer, they are the heaviest one which appear here. And the tetramer, we see that the S is formed in excess, but as we move to the 6 and the 7 and the 8 and the 9, there is reversal. And this reversal in the enantiomeric excess in keeping with the formation of the racemic beta sheet. Now, the reason why I mentioned that experiment, because I thought that if this is the mechanism that the reaction can continue, can operate, then why doing this in a crystal? You can go in water. In the beginning, we are going to obtain some distribution of oligopeptides of certain composition, of certain diasteromeric composition, and in principle, this, once we form tetramers, pentamers of homochiral sequence, they can self-assemble together to form this racemic beta sheet, and this racemic beta sheet can can exert asymmetric induction in the ensuing process of chain formation. Now the formation of the racemic beta sheet has a very important advantage, because if you want to form an helix, you have to have 8 repeat units of the same endogens. If you want to form a beta sheet which is pleated, you need 8 repeat units. But if you want to form a racemic beta sheet, you need 4 to 5 repeat units. And therefore you're reducing actually the number of repeat units which are needed in order to form this particular helix or this particular beta sheet, which can now enhance the formation of the. It was George Wald, he's the Nobel laureate for the chemistry of vision, which proposed in the 557 that maybe helices can somehow enhance stereospecific polymerization. Andre Braque was thinking in terms of beta sheet, and the problem of the time that might be the first species that are formed on Earth that have preceded the alpha helices. So now, for that reason, we decided first to start the polymerization of these molecules like phenyl and carboxyanhydride in solution, which are water soluble, and then we tried to repeat first experiments which have been done during the years, especially at Harvard by Alkanab Laut, Paul Doty, at the Weizmann Institute by the School of Kachalski, but they were interested in the synthesis of peptides, and therefore their reactions were performed in organic solvent. Now, by repeating the conditions of their reaction in THF, what we could find actually, that they form actually heterochiral, that is binomial distribution in certain sense. But if you do the same polymerization in water, this is in the case of valine and carboxyanhydride, you could see that the distribution of diastereoisomers is completely different. Whereas here you don't find the wings in an organic solvent, but as you go to water, you can see that the wings are pumping out. And in particular, for example, the reaction with leucine was remarkable. The reaction with leucine was really remarkable, because you could get up to 24 repeat units, and you can see here, actually you're getting only the wings and wings -1. And with my friend in Paris, Gerard Bolbach, who is an expert in mass spectrometry, and since mass spectrometric analysis are very careful, we are doing the experiments both in Rehovot and in Paris. But Bolbach has also the Maldi-Tov-Tov way to analyze this particular cell, and he could show that this N-1 is in the two wings of the chain. Either the chain starts with one wing, with one molecule which is heterochiral, or there is a termination of the heterochiral molecule of the growth of these particular chains. So this was done with N-carboxyanhydrides. These N-carboxyanhydrides, we have to synthesize them, and we have to do this already, and I don't know how relevant is this to prebiotic part. But we wanted to perform these experiments in water, and we were actually impressed by the work of Luigi, and I think Jonathan actually modeled the experiments of Luigi. But the Luigi experiments, okay, these are beta sheets. Okay, sorry, I don't know how much time I will pass the time. I can have another
Minus
5
10
minutes.
minutes, but go
Okay,
ahead.
5-10 minutes time. No,
Said minus
I was
10,
very
you had a
gracious to
little
you,
longer.
remember? I was very gracious to you.
You were,
Chair,
sure. Turnabout is fair play.
Okay. Well, there is another point here which proves that we have the beta sheet, so I shall, if I have 5 minutes, I shall come
Sure.
back.
Yeah.
We could do that, the X-ray diffraction of that, which fits actually to beta sheet, but we could not differentiate between racemic beta sheet and pleated beta sheet in this particular system. What we could find was, by analyzing the water-soluble peptides, what we found that we could, the homochiral peptides, 4, like here 4 and 5, are not soluble. There was the 4 and 5 and 6 are not soluble. So what we are assuming here, that they actually precipitate, and indeed you can see that during the polarization reaction, there was the formation of some kind of colloids, and the reaction continue in the form of colloids. So we are asking ourselves once again, if this is a racemic structure or this is an antiomorphous pleated. But as we said before, a pleated one, if we want to crystallize that, the rate of crystallization and precipitation depends on the concentration of the R, and this will depend on the concentration of the S chain. Whereas if we are crystallizing in the form of a racemic compound, like in crystals, actually the rate of crystallization is actually to the square, because it depends on the concentration of the R and the concentration of the S. And therefore, and then my colleague Kobe Levy now has performed some Monte Carlo studies based on the models of the racemic one, as I pointed out. Linus Pauling actually proposed on the basis that this kind of racemic beta sheets should be stable. He called them the ripple beta sheets, and energetically they are very, very similar. But again, you see here, if it is a racemic structure, the rims of these structures are homochiral. And what's one of the enantiomer will grow in one direction. Okay, all of them of the same go in one direction, whereas the other one will go in the other direction. And therefore, they can, the green can recognize the one endedness, the red can recognize the other endedness. And these are, as they pointed Pauling and Corey, this in 1953, when they published all the 10, they also proposed this kind of, they call it the ripple beta sheet architectures. And now if you have here, again, a molecule of opposite endedness here at this time, it can induce an enantiomeric cross inhibition. And therefore, if these are the racemic beta sheet, you expect that the first one, the short peptides, will be enriched with peptides of the same endedness as that of the initiator, whereas the long one, there will be of reversal. There will be what they call kind of an enantiomeric cross inhibition. These are the sites which are hydrated, the molecules themselves are hydrated, and therefore they can read that the stereomeric recognition should be very, very important. Again, with the same mechanism that we did in the crystal, we try to do this in this particular experiment in water, and you can see in the case of valine, you can see that if you start with L-valine on methyl ester, the short one and enrich with 1, whereas after reaching the tetramer and pentamer, you have a reversal of the enantiomeric axis of the system. If you go to solution, and if you polymerize S-valine with L-methyl ester and S-valine with R-methyl ester, here you have to form the pleated sheet, because you don't have any other alternative. And if you compare, let's say, if you compare the formation of the lungs, if you like, if you compute the enantiomeric axis, if you normalize it to one of the peaks, of the big peaks here, you can see that the enantiomeric axis here is in favor of the S in comparing that when it was done with the R enantiomer. So it seems that the R enantiomer can, in this case, when the pleated sheets are formed, the R inhibits or impedes the growth of the S chains, whereas in the case of the racemic, it's just reverse, and on the basis of this kind, we concluded that we are dealing with racemic system. Now, at that moment, we ask ourselves, because as I pointed out, Luisi did some studies on this polymerization of amino acids using the Orgel reaction. Orgel reaction, actually, Orgel used this is the Stab reagent, and used the polymerization of glutamic acid and other systems, and Luigi was doing similar studies that we were doing on the air-water interface and in crystals by, again, similar labeling system. And this reaction is that you take the pure amino acids, you react them with carbonylimidazole at 0 degrees for 3 minutes, and you're creating this intermediate, and then, according to what we have not been able to isolate the N-carboxyanhydride, but some people assume, and Orgel assume, that you're forming N-carboxyanhydride as an intermediate. We are now searching for this intermediate by fast NMR methods. And then if you polymerize, then you polymerize, go to the polypeptide system. Now what Luisi studied several systems, but if you go now to the leucine, we could get up to 6 hexamers, but he uses as the initiator the amino acid itself. Because if you add the amino acid itself is a sweeter ion, the concentration of the amino acid of the pure amino acid NH2 is very low, and now we have done some NMR studies on these systems, and we can see that the polymerization competes very seriously with hydrolysis. Because in the hydrolysis is very fast in the system, and what Luisi does, he always adds N-carboxyanhydride to the system in order to get this, and he gets some up to hexamers. In the case of tryptophan, he was able to get up to decamers, but adding a lot. But as you can see, these hexamers are found in they are accounting for the binomial distribution, but they are not the central, the major component that you find in the system. Now we ask ourselves, what is the difference? If we take leucine and we can get 30 repeat units, and the 30 repeat units are almost the single product, where is the difference between our reaction and the Luisi reaction? And there were 3 different points. First of all, it uses buffer. We noticed that if you perform the reaction of the polymerization, the pH doesn't change of the reaction. It is almost changed very slightly. Now, but we say maybe what we can do is to add the initiator to the system. Because if I want to prevent the hydrolysis, and if I had the initiator into the system, of the first stage, then at a certain stage of the reaction, and there is a problem there, but I think that it works, that if you add the initiator, you can promote the polymerization as against the hydrolysis reaction. And indeed, if you take this system here, and you polymerize, I don't know what's happening here. I think I missed here one. I think the results were very similar. The results by doing these experiments were very similar. I think that for some reason I missed the other slide, but the slides are very similar. You could get up to 24 repeat units if you do this experiment in the presence of initiator. Okay, if you add the butylamine or you take one of the esters of the amino acid, you can get up to 24 repeat units, and they are really kind of like in the pure N-carboxyanhydride that you found in solution. Okay. Sorry for that. No, it is here. The spectrum is here, sorry. Here is the spectrum. Okay, so I will go ahead. Now the question was, again, and I would like to end with that, the question was whether we can generate, again, we proved that we have beta sheets in the system as well, like in the pure carboxyanhydride. But our central question was, we want to prepare copeptides. And the question was whether this beta sheet that we are generating, can they recognize between amino acids of different structure, but of the same endedness, but they cannot recognize between heterochiral molecules, heterochiral amino acids. In other words, if they recognize this beta sheet can recognize, this pocket can recognize between, let's say, L-tyrosine, L-histidine, L-alanine, for example, but they cannot recognize between the D of these molecules, then what we can do, we can take a mixture of the amino acid in water and polymerize that, and level the L again with one of the deuterium, and as you polymerize that, you get mixtures of poly-L copeptides, and you take poly-D copeptides, and then in this case, if you find in the second stage how to enlarge these polymers, maybe we can get polymers that may operate as some kind of very primitive enzymes for the, and we have seen this by Cordova, very nice result this morning, that amino acid and peptides can really serve as very nice catalyst for asymmetric synthesis. So the first experiment that we did the polymerization of D-isoleucine with L-leucine. And we did it also L-isoleucine with L-leucine, D-isoleucine with L-leucine. And by doing again, labeling one, of course, because they have similar molecular weight, then if you take, let's say, the L with D and the L with L, you get very different distribution. If you take L with D, D isoleucine polymerizes separately, L isoleucine polymerizes separately, as is expressed here in the molecular weight of the system. On the other hand, if you take the L isoleucine with L-leucine, and you take L-leucine ometoxy as the initiator of this amino acid, you can see that you get a binomial distribution between the leucine and the isoleucine. We try to do the same thing with histidine, but due to this, cost, we find Peter LahavC was doing some polymerization reaction in solution, and he told that it is impossible because histidine gives the urea if you want to react it with N-carbonyl. But if you take the N-methyl, N-methyl histidine, and you take L-phenylalanine, again you find this very nice binomial distribution, although the histidine, which is hydrophilic, does not form the peptide. You're forming mixed copeptide, and if you take the phenylalanine with diphenylalanine with the L, you can find only the diphenylalanine form here. The L is not forming the peptide. So this was a nice example for that. Okay. Okay. And then what we did several systems. The mass spectra are very complicated. So if I show you the mass spectra, my friend Helmut Schwarz from University of Berlin once told me there are two types of slides. One slide is to inform people and one slide is to impress people. So if I'm going to show you the other one, I will only impress you. But we have selected this example, D-phenylalanine, D-tyrosine, D-alanine, initiated by butylamine 25%. And you can see now, we can find the D-phenylalanine tetramers. We can find phenylalanine alanine, the wings again, which is a copeptide. We can find phenylalanine tyrosine, the wings, again phenylalanine 5. And we can find alanine, tyrosine, phenylalanine. Phenylalanine, all of them, the L and the D, are found under these particular conditions. I'm not saying that all amino acids will go into this particular part, but this is a nice way that the mechanism that we are proposing is that we are forming some of the short homochiral peptides, and the mechanism that Jonathan has proposed of having what they call is Markov control in the first stages of the polymerization. In other words, if you want to translate this to asymmetric induction, to organic chemistry, the chain at the early stage induces asymmetric induction to the system to create these short oligopeptides 5 and 6, where the homochirals are formed in some excess in comparison to the binomial distribution. Once these are formed, they form a racemic antiparallel beta sheet, and the chain elongation of this beta sheet is done within these particular beta sheets, which allow us to have some separation of peptides. Now the point is that once we can generate homochiral copeptides, and if you can take one of the enantiomers in small concentration. As a matter of fact, these chains cannot be any more racemic, because if all the sites are different, and if the small components are distributed between the different chains, actually we are ending up with non-racemic mixtures of these particular peptides. And our current interest is now how to find ways how to elongate these chains and to get to a certain size and to start searching by combinatorial methods for some kind of peptides which might operate as enzymatic, which might have some enzymatic properties. Okay, now I think this is, I would like now to thank the first part of the glycine, as I pointed out, was done a number of years ago. But since, as I say, that there are people like Professor Saito and Raphael and others, I wanted to present that model because although it was done long ago, even before the Kondapudi experiment on the sodium chloride, it has been ignored, actually. And I wanted in this discussion to try to revise it. And this was done with my colleague Professor Lezerovitz, Leah Dadi, Ziva Berkovic, Edna Gatti, and Isabella Weisbuch. The last studies, which are the current studies, this is to impress you, actually. Okay. It's done by my colleague Dr. Isabella Weisbuch, Irina Rubinstein, Ron Iliash, this student that came from Argentine, and Ron Elias that is with me. I collaborate with Gerard Bolbach in Paris 6 in the case with the mass spectrometrical analysis, and Christian Kerr that these studies that we have done on the air-water interface. Thank you very much.
Questions?
I would like with Jonathan have a discussion, because you just published your model of the polymerization of these chains using the Louisi reaction. You're going to speak on that after. Because I think that it would be nice, and I think one of the advantages of this meeting was to try to find the differences between the two ways, whether one can really find ways how to model also this formation of these data sheets.
Second question, where do you put your label for the mass?
We buy that. We have 10 deuteriums for the leucine, and we did a very careful studies in the beginning.
Where they are located?
The side chains, all the side chains. But with the long chains, where we incorporated 30 deuteriums, 38 deuteriums, we were very careful to see whether you can perform a quantitative analysis between the wings. And we had long discussions, including with Professor Tabe and others, that in the beginning they were quite skeptical whether this is possible. But in principle, I think you can compare now. We know that because by making some reference system, you can compare between the concentration of the wings for a given dimer, trimer, tetramer, and pentamer. In principle, some people claim that you can do it between the different molecular weights, but we are not doing that. Okay.
In your, it's not, it's very elegant. Thank you. Yeah. But the methionine lamellae, where you get homochiral lamellae, and then so as one lamella grew, it would exhaust its enantiomer, and then the other one would nucleate on that one and grow. Did you do any experiments to determine what would control the thickness of the individual lamellae?
No. I think that we know that we look also in other examples, because you know that X-editing does the same thing. Joyce published another paper in the case of the sugars, but we have not done that. We were interested to try to prevent it, but we are not looking on that. My feeling is it will depend very, very much on the relative concentration that emerges during the process of the crystallization. In other words, if you do experiments with excess of L, excess of D, in different concentrations, maybe you can learn something.
But it might depend on the depth of the solution that's crystallizing, or on if you could use a mixed solvent so that you could change the total concentration
of the solution
of the DL. And then the question is over over a short distance, you might be able to get diffusion that could keep the same one growing, but over a long distance, diffusion might be impossible. So if the solution that was growing was very dilute, it might be different from if it were concentrated.
What you're suggesting is to try to have control on the degree of saturation of the system, or to keep the concentration low in order to prevent the other ones to proliferate.
Yeah. This is not directly on the subject here, thing, so maybe we should talk about it later, but I think it's worth it.
I think it's important because
it might be possible to control the things.
Because I think this point, I brought that example because I think it is relevant to the question which was raised here in the various model of the grinder. Because everyone assumes that there are clusters. And I think that even we have other experiments that we have done by growing the clusters at the air part of the interface. You can have their trimer, tetramers. For example, if you put an alkyne, you can get up to 20 layers. Or you can get small number of layers. And if you have an additive, you can see that this cluster actually disintegrates. Now, we had a system where you have 3 polymorphs, and you put an additive and you describe 2 polymorphs in one. So what I wanted to raise, and the reason why I raised it, because you cannot explain this removal. You cannot explain the removal of the lamellar twinning by assuming single molecules. You must have clusters. In these clusters, you can remove them by an additive.
Okay. I think we have, Sanko?
In the recent case, they are structures
Of the glycine?
Glycine. Why 010 phase is always R and 01 bar 0 phase is...
No, what I say is the following. I understand your question. The point is that you have layers, okay? Let me just have the slide.
It may happen that the crystal growth stops in between.
No, I know, but I know what you mean.
2 R's in
No, I will try to explain
why.
why.
Why doesn't that happen? That's my simple question.
Okay.
If it is polar, it is rather
No, I know the just follow. I understand your question. I think I understand.
Sorry.
Okay. Now, what I say here is the following. This phase has to expose, first of all, the R and then the S. The R and the S. This is what you mean, right?
Yes.
Yeah, but if it exposes the S here, it will not recognize an R molecule. In other words, if it exposes, let's say, the S, it will recognize the R molecule. Okay? But if you take this S here, and you try to put another S here, which likes to go with this group in this particular layer, it has to enter with this group here. So the S layer will not recognize this S molecule. You see what I mean? Because this S has to enter into the S layers of glycine. Because this is the same configuration as these particular layers. Okay? So if this molecule, when this crystal exposes the S layer, okay, it will not recognize the S molecule because this S molecule...
I don't mean that. I don't have any amino acid. I only discussing glycine.
No, then this is not... the reason why I wrote it, if you're asking, because this is known that the alpha glycine grows by pairs. It has been shown, because if you measure, let's say, the length, the size of this step here, it is a dimer, not a monomer. Michael Ward and others have done this. Leslie Zerovich has done the fraction of this crystalline systems, and we know that these crystals of alpha glycine are growing pairs.
So it's a atomic layer.
Yeah.
Okay, then it's all right. It's all right.
Okay.
Sorry, I thought it has a macroscopic size thickness.
No, this is not like zinc sulfide. In zinc sulfide, you have in one side you have sulfur, and one you have zinc. Yes, Joseph.
I wonder if there is some reason for this pairing or for this in the homosexual. It seems that it's a normal situation that when you are losing symmetry with the homosexuation, but you lost and you recuperated the impact. Because when you imagine the growing of this one, that is, the glycine is a chiral, so-called chiral, and then they make or a monodimensional or a bidimensional to the chiral, but the next one try to recuperate the centrosymmetry.
Well, I would like to answer your question. I understand your question.
Report.
I would like to answer your question. What we have done, and I didn't have time to discuss that, we grow a crystal, okay, and you do the crystal structure of that mixed crystal. So what people used to do before we came with these ideas, they were actually averaging. And in just a moment, and they were averaging and they say the distribution. But now what we are doing, we are actually sectoring the crystal. You take a crystal and you sector it. And you do the X-ray analysis of each one of these sectors. And you see exactly where these molecules are residing. If you take, let's say you take asparagine, aspartic acid, you can have there about 12% of the aspartic acid going through the crystal, and you can see that aspartic acid is going on specific sites, reducing the symmetry of the system. We have also done some kind of non-linear optics measurements, but in the system to try to find where these molecules are standing. So they are creating some defects in the crystal, but
No, I agree totally with it. It's only a general comment,
No, but I want to
that it
understand
seems
from-
that to go to a chiral homoassociation,
yeah,
it seems that this homoassociation process, because you lost symmetry, and then in the next test they try to recuperate symmetry, and then she lost in the next aggregation.
Yeah, but
it seems that there's a competition between to lose the symmetry.
no, but
and
if
to
you have an
gain symmetry.
autocatalytic process, like the Soy reaction, if you have an autocatalytic process, or like many other autocatalytic processes, and this is an autocatalytic process,
Yes.
then you are away from equilibrium.
Yes, no, but it means in respect to the symmetry point of the aggregation, that it seems that you lost and try to recuperate the symmetry. Then in some cases, then it is no more possible than you have the conglomerate. But because it is very, and you have also the limit example, this is the clusters association with this one. It must be some general rule.
I'm not aware of these things.
Okay. So we'll have coffee until 4 o'clock.